Hi, I'm Kun-Ting Chen. Today I'm excited to present to you a breakthrough discovery of our work. Geographic and natural data can interactively wrap around 2D sphere and supports data analysis tasks. The overarching goal of this research is structured into two studies. First, we investigate the effect of interaction on different map projections. Second, we investigate a related idea that networks can be drawn on a 2D sphere or torus and presented in interactive projections. There are many methods for projecting our Earth onto 2D sphere for better readability of maps on 2D screens. However, it is inevitable that distances or shapes are more distorted near the edge than they are at the center. Moreover, path or distance discontinuity has been shown confusing. Therefore, distortion and discontinuity may significantly limit the usability of 2D maps for geographic comprehension tasks. A network can be drawn on 2D sphere or torus. The benefit is there's no longer notion of central or peripheral nodes on these topologies, as the layout can be centered at any node of interest. One disadvantage, however, is that the link discontinuity is inevitable on these topologies. One way to find better solutions to the problematic distortion or discontinuity issues in maps is to introduce continuous spherical wrapping. A user can use mouse or touch drag to move any node of interest to the center to have a less distorted view than they are at the edges. In our first study, we compared 5 different projections with and without interaction across 120 participants. We find that for distance comparison, interactive projections are always more accurate than any static projections, but slower than static. On the other hand, the choice of projection makes less difference. Among interactive projections, we find orthographic hemisphere, being the most naturalistic, like a 3D globe, is more accurate than equal Earth or hammer. For direction estimation, interactive is again overwhelmingly more accurate than any static projections, but slower than static. The choice of projections makes less difference. Orthographic is found to be more accurate than equirectangular. Equal Earth, being a continuous projection, is slightly faster than Morley hemisphere, which splits the maps into 2 separate views. For area comparison, interactive projections is more accurate than the corresponding non-interactive projections, but slower than the static. Equal Earth is slightly faster than hammer or equirectangular with small effect sizes. For networks, interactive projections can be used to reduce discontinuity or distortion. How best to present a network on a 2D sphere and how it performs compared to standard node-link diagram or 2D torus layout remains an open question. Using the most successful projections from our first study, we created visualizations of network layouts using equal Earth and orthographic projections for our study trials. We first adapted a common 4-stilted layout approach to lay out a network on the sphere, and then apply equal Earth and orthographic projections to project the sphere onto a 2D plane. We proposed a heuristic to automatically find the best rotation that minimizes the wrapping links. The resulting visualization shows that the cluster boundary is made clear in such representation. In our second study, we compare sphere network layouts to standard flat node-link diagram and 2D torus layout. We find that both 2D sphere and torus are more accurate than standard flats. Within continuous topologies, we find that equal Earth and torus are more accurate than orthographic hemisphere. Participants mentioned that equal Earth and torus provides a great overview of the entire network. Although equal Earth involves link distortion, the clusters are made clearer in one single view, while orthographic hemisphere, they fundamentally close the clusters by connecting two separate spheres. For path-following tasks, we find that flattened torus are more accurate than equal Earth and orthographic hemisphere. Participants mentioned that the straight links in flat or torus made it easier to follow the path, while the curved links in equal Earth and orthographic increased the difficulty, especially at the edges due to the distortion. To our surprise, previous work on map projection studies have been mostly for static display. There has been no research into the effect of 2D interactive map projections on geographic comprehension tasks, but the results are promising. The takeaway message is, interactive map projections should be used more often. The choice of map projections makes less difference. For networks, interactive torus wrapping works really well. In future, we are interested in exploring other types of data that wrapping topologies make sense, and exploring real-world usefulness in wider social or biological networks applications. This is an oversimplified presentation. For more details, please refer to our paper. I would like to greatly thank my awesome collaborators and numerous contributors who made this work possible. Thank you for your attention. We are happy to take any questions.